everyone, welcome back to the Applied Physics lecture series. This is Dr. Y. Anantha Lakshmi. Today we are going to discuss about the stopping potential and kinetic energy in the photoelectric effect. In our previous lecture series, we have come across the photoelectric effect, matter waves and its properties, and also the dual nature of light. Today in this session, we are going to discuss about the stopping potential and kinetic energy in the photoelectric effect. The overview of today's session is the stopping potential, the maximum kinetic energy of an electron, and the effect of intensity and frequency on the stopping potential. Here, our interest in the photoelectric effect is to define two things. One is the counting the number of electrons coming out per second. The other one is calculating and measuring the stopping potential and maximum kinetic energy of the electrons. We have come across what is the photoelectric effect and the experiment related to the photoelectric effect in our previous session. Now, in this session, our interest is to find the counting the number of electrons coming out per second and also calculating and measuring the stopping potential and maximum kinetic energy of the electrons. Now, how do you find what is the maximum energy with which the electrons coming out per second? For that, let us recap the photoelectric effect experiment setup. Okay, here is the experiment setup. You can recap once again. This is the metal which is acting as an emission of electrons, and this is the collector. The collector collects the electrons emitted from the emitter and attached to a galvanometer and a potential voltage source. Now here, when this metal source is illuminated by a light source, then this metal emits electrons which are collected by the collector, which we have already come across in our previous session. In this session, our interest is to study the stopping potential and as well as the kinetic energy in the photoelectric effect. See here, when the metal emits the electrons, whatever the amount of electrons are emitted by the metal need not be collected by the collector. 1 or 2 electrons can be lost. It means that the number of electrons emitted per second is not exactly equal to the number of electrons collected by the collector per second. So here, from this experiment, we can observe that what is the thing, how our interest is to find out the number of electrons emitted per second, which indicates the kinetic energy of an electron. So, from this experiment, we can observe that what we can notice from this experiment, as the metal is illuminated by the light, the electrons emits. That is one point. The other one is when the voltage is increased. When the voltage is increased, see here, one thing, photocurrent we are going to calculate from this. When the metal emits when the emitter emits the electrons, the collector collects these electrons. Then the number of electrons collected by the collector indicates the change in the current in the galvanometer. These currents also depends upon the voltage. As the voltage is increased, current slowly starts increasing, and at a certain voltage, we can observe that the current, the photocurrent reaches to the maximum. That particular maximum current is called as saturation current. As the voltage starts increasing from V1, V2, this is the negative potential, and we are concentrating on this saturation currents here. As the voltage starts increasing, the current slowly increases and reaches to the saturation at a certain voltage. This saturation currents indicates that the number of electrons collected by the collector per second. This saturation gives us the information about the maximum number of electrons collected by the collector per seconds. Now, this indicates that this maximum current is the direct indication of maximum number of electrons collected. But here our interest is to study the stopping potential and kinetic energy in the photoelectric effect. For that, what we need to do is here to study the stopping potential, let us flip the terminals of this voltage. Let us flip the terminals. Then what happens? Then whatever the electrons are emitted by the emitter will not be collected by the collector. As there is a same sign, these electrons get repelled. So whatever the electrons are emitted by the emitter will not be collected by the collector. Not only this, from this also it indicates that there is no change in the current. Not only this, when if we vary the voltage also, you can notice the change in the photocurrent. See, as we increase the voltage in the negative side, the current becomes smaller and smaller and becomes zero. See, if we increase the voltage from V0, V1, V2, V3, that is 1 volt, 2 volt, 3 volt. From at 1 and 2, we have noticed that the current becoming small, and at 3 volts, we have noticed that the current becoming zero. This particular voltage where the photocurrent becoming zero is called stopping potential. See, the potential where the current becomes zero is the stopping potential, or we can even call it as a cutoff potential. Therefore, the stopping potential in the photoelectric effect is the minimum negative potential of the anode that stops the photoelectric current. It is also known as the cutoff potential. In order to study the stopping potential in the photoelectric effect, what we did here it is, we are flipping the voltage terminals so that the same sign will be observed near the collector. As there is a same sign, there is a repulsion between them, and whatever the electrons are emitted by the metal source emitter will not be collected by the collector. For that, let us consider, in order to measure the kinetic energy, we have noticed what is the stopping potential where the photocurrent is becoming zero. Now our interest is to measure the kinetic energy. For that, let us consider a small example here. It is noticed that the current becoming, see, in our previous example itself, we have noticed that the current becoming zero upon increasing voltage from 1 volt to 3 volt. Here the potential difference is 3 volts. This potential difference is the direct indicates that how much energy is gained or lost by an electron when moving from one point to the another point. Now, at this 3 volts of stopping potential, the charge that the electron is gaining or losing is the charge is nothing but the electron gaining or losing 3 joules of energy per second. Then, as the photocurrent becomes zero, the kinetic energy of the fastest electrons must have 3 joules per coulomb. See here, at 1 volt, we have noticed that the photocurrent becoming slow. But there is still the collector collecting a few electrons, or the electrons reaching, or the electrons, see here, reaching to from emitter to collector. At 2 volts, we have noticed that the fast pacing electron reaching the collector. It means that still we can notice a negligible currents. Now, at 3 volts, we have noticed that the electrons reaching the collector reaches the collector, fast pacing electron, and turn backs. It means it diverts the direction and turn backs. This turn backs indicates that the current becoming zero. So at 3 volts, we have noticed that the current is becoming zero. At 1 volt and at 2 volt, a negligible amount of current is observed in the galvanometer. So here, what is happening? This particular energy, whatever we have considered here, is 3 joules per coulomb. This particular energy is the energy of a fastest electron reaching the collector. So, if the electron having 1 coulomb of charge, then the kinetic energy of a fast moving electron is represented as 3 joules per coulomb into coulomb. If it is having 2 coulombs of charge, then 3 joules into 2 coulomb. In similar way, if it carries 10 coulombs, then 3 joules into 10. But here we are concentrating on a single fastest electron, how much kinetic energy it has carried. So, for that, the kinetic energy is 3 joules per coulomb into the charge of an electron, which is nothing but 1.6 into 10 to the power of minus 19 coulombs. And upon simplification, we are going to get the kinetic energy as 4.8 into 10 to the power of minus 19 joules. This particular kinetic energy, whatever we are talking here, is applicable only for the fast moving electrons. Upon reducing the voltage, increasing the voltage also, we have noticed that few electrons reaching the collector. So, that few electrons are considered as the fast moving electrons, and this kinetic energy, this applicable for the fast moving electrons. Therefore, here the maximum kinetic energy of the fast moving electrons is 3 electron volt. 4.8 into 10 to the power of minus 19 joules is converted to the electron volts, which is nothing but maximum kinetic energy is equal to 3 electron volts. Therefore, the stopping potential is equal to the maximum kinetic energy of an electron in electron volts. Next, coming to that is the one way of calculating the maximum kinetic energy. The another way of calculating the kinetic energy is if E and P are the energy and the momentum of a photon of the incident light, then nu and lambda are the frequency and wavelength. Upon simplification, we are going to get the maximum energy by considering E is equal to Pc. P is the momentum and C is the wavelength of the light. So, velocity of the light. So, here upon simplification, we are going to get the kinetic energy as K max is equal to h nu minus pi. Here where pi is the work function of the metal. Whatever the metal considered, it is the work function of the metal. This is another way of calculating the maximum kinetic energy. One way is by considering the charge of an electron, we can calculate the kinetic energy in this way. The other way of calculating the kinetic energy is by considering the equations of E is equal to h nu. We are going to get the maximum kinetic energy K max is equal to h nu minus pi, where pi is the work function of metal. Next, let us discuss about the effect of intensity and frequency on stopping potential and kinetic energy. In order to study this effect of intensity and frequency on stopping potential and kinetic energy, we will consider two cases. The first case is intensity decreases, frequency of the light remains same, and the second case is intensity increases and frequency decreases. These are the two cases. For this, let us consider the first one, intensity decreases and the frequency of light remains the same. If the intensity is decreased, what intensity is decreased here? The intensity of light is decreased. The intensity of light is decreased means what is happening? What is happening here? The emission of photons from the light decreases. Frequency of the light remains same. As the frequency is remaining same, what is happening? The energy of the electrons, the energy of the electrons remains same. Whatever the energy the electrons are emitted will be, the energy remains same as it collects the same electrons. One thing when the intensity is decreased, what is happening? Number of photons emitted from the light decreases. As the frequency of the light remains the same, as the frequency is remaining same, what is happening? Whatever the energy is carried by the electrons remains same. See here, since the frequency is the same, the energy of the electrons remains same. From the equation, we can say that E is equal to hf. As the frequency is remaining same in this equation, the energy also remains the same. This means that the input energy and the output energy of an electron remains same. Whatever the input energy, that energy also remains same, and the electron coming out also will be with the same energy. Next, but the number of photons reduce. Why the number of photons are reducing here? As the intensity of the light is decreased, the number of photons reduces. This reduced number of electrons emitted from the emitter in turn gives the current also reduces. Means what? Whatever the electrons, the energy is remaining same. The count of the electrons is decreasing. this decrease in the count of the electrons decreases the photocurrent. Therefore, the saturation current decreases due to the less number of electrons coming out. See here, when the saturation current will be more, when the number of electrons, the count of the electrons is more. Either the electron 1 is released or the electron 10 are released, the energy remains the same. But here, as the intensity is decreasing, whatever the input photons are decreasing, the count of the photons also decreasing. This decrease in the photons, giving the less count is going inside the metal. Then the electrons emitted by the metal also decreases. The number of, the count of electrons decreases, but the energy remains the same. This count of electrons in turn decreases the photocurrent. So, the saturation current decreases in the case of in a high intensity and the frequency remaining same. So, this is the graph here. See, this is our initial saturation current graph. As the intensity is increased, decreased, the saturation will be decreases to this level. This is our next graph. Though the energy remains same, the photocurrent decreases. Similarly, this decrease in the photocurrent eventually decreases the saturation current at low intensities. Next, coming to the next case. Intensity of light is increased and decreases the frequency. Here what we do in the earlier case, we have not changed the frequencies remain same. Here we are varying both. The intensity of light is increased. Parallelly, there is a decrease in the frequency. It means that as the intensity of light is increased, then the number of photons emitted from the light also increases. Next, decrease the frequency. Decreasing the frequency indicates that the energy of an electron decreases. The energy of an electron decreases. Though there are more number of electrons emitted, but the energy is decreased as the frequency is decreased. So here, the intensity of light is increased indicates that more number of photons. We are giving more number of photons. More number of photons are released from the light source, and these more number of photons we are instanting on a metal surface, and that metal surface, from that metal surface more number of electrons are emitted as more number of photons are absorbed. Is it clear? Then when more number of photons are absorbed and more number of electrons are released, but the energy of an electron is remaining small as the frequency is decreased. See here, if frequency is small, the energy of photons is small since they transfer less energy. Though more number of electrons are given, as the frequency is low, they transfer less amount of energy. Because of this, though there are bulk amount of electrons are emitted, the energy of all these electrons is going to be remain very less. The current increases with intensity. Here, the current, as the number of electrons are emitted, the photocurrent is increased here in this case and reaches to the saturation at larger values of stopping potential. See here, at the higher intensities, this is our initial graph when no modifications is done either for the intensity or for the frequency. Here, now, in this case, we have modified or increased the intensity. So, at higher intensities, the stopping potential should be more. Why? Because at higher intensities, the photocurrent is also more. In order to bring that photocurrent to the zero, stopping potential is nothing but where the photocurrent is becoming zero. So, the stopping potential will be more here in this case as the intensity is high. and this is the case where the intensity is low. At the higher intensity, the frequency is less. And at lower intensities, the frequency remains same. This is all about the stopping potential, maximum kinetic energy, effect of intensity and frequency on the stopping potential, and kinetic energy. Here, in today's session, we have discussed about the stopping potential, how to calculate the maximum kinetic energy. Stopping potential is nothing but the minimum negative potential of the anode that stops the photoelectric current, which is also known as the cutoff potential. And we have even discussed about the effect of the intensity. If the intensity is more, how will be the stopping potential and the saturation currents, and if the intensity is less, how will be the photocurrent and as well as the stopping potential. Thank you.